Okay, so enantiomers are chiral molecules where one enantiomer is the mirror image of the other and they're not superposable like your left and your right hand. Enantiomers, the physical properties, are the same in many situations. So the melting point is the same, the boiling point is the same for one enantiomer as the other. They rotate plane polarized light in opposite directions but equal magnitude. And they react with achiral reagents the same way. So these are, most of the reagents we use are achiral. We can use D or plus or L and minus to talk about the way that they rotate plane polarized light, but that says nothing about the actual configuration of the atoms. It doesn't tell us whether we have the right hand or the left hand. Okay, so if we know the structure, on the other hand, we also can't say from the structure whether that molecule will rotate plane polarized light to the right or the left, although very high level computational chemistry is getting much closer to doing that on a regular basis. So how do we talk about the configuration of organic molecules in terms of the actual three-dimensional arrangement of the atoms? We need to use a set of rules to talk about those molecules. So the rules we use are the Cahn-Ingold-Prelog Rules. And this allows us to assign a letter to one mirror image versus the other mirror image. And the letters we're going to use are the letters R and S, both capitalized. So the sequence and the way in which we go about this is, firstly, we locate the chiral center, the stereogenic center. Then we assign priority to all four of those different groups attached to that chiral center, from 1 being highest to 4 being lowest. And the rules are very similar to E versus Z alkenes. We're going to assign in order of atomic number. The higher the atomic number, the higher the priority. So for example, bromine has a higher atomic number than chlorine, and so bromine will be a higher priority than chlorine. If we find a point at which there's two atoms with identical atomic number and therefore identical priority, we go further out along the chain until we find the first point of difference between them and assign the priority that way. So the atomic number of the atom that is directly bonded is how we assign the priority. If the same atom is bonded, we go to the next atom and so on. If we have multiple bonds, what we do is we treat them as if they were actually atoms in place of those multiple bonds. So these are what we call dummy or phantom atoms. So in the case of a carbon-oxygen double bond, the carbon, we replace this second bond with a bond to a dummy oxygen atom, like so, and we replace this bond that the oxygen has back to carbon with a dummy bond to a carbon atom, like this. If we had a triple bond, like this nitrile here, we have two dummy nitrogens bonded to that carbon, and the nitrogen has two phantom carbon atoms bonded to it. And so we end up with that sort of structure in terms of assigning priority. So we need more rules than just that. Once we've determined the priority of the groups, what we do is we put the lowest priority group away from us. So it's really important that we have to direct the lowest priority group so it's pointing away from us and into the distance. We then look at the remaining three groups and orient them in a way that they go from highest to lowest, 1, 2 to 3. If they go from 1 to 2 to 3 in a clockwise direction, then we call that compound R, which is from the word rectus. If they go in an anti-clockwise direction, then we call that S for sinister. And the way to remember this is, imagine driving a car and you come up to a right-hand turn, then R is going to be where you make that right-hand turn. Okay, so if you're going to make a right-hand turn in a car, then you're going to turn the steering wheel clockwise to make that right-hand turn, and so that one is R, clockwise. S is where we go the opposite direction. So as long as you remember R as a right-hand turn in the steering wheel, then you'll be good to go, clockwise. Okay, so once you've worked that out, if you want to know the stereochemistry of the other enantiomer of the compound, you don't have to go through the whole rules again, because we know that everything gets made into the mirror image. the molecule then will have the opposite configuration. So if you assign configuration to a molecule as R, you immediately know that the enantiomer of that molecule is going to be S without having to redraw it. So let's practice that with a couple of examples. We've got the absolute configuration of these molecules here. Let's have a look at the first one. We've got a molecule with a hydrogen here, lowest priority, a carbon atom, a chlorine, and a bromine. So that's order of priority. Now, fortunately, this one has the lowest priority group already pointing away from us. So this is going away, and the remaining groups are going in a anti-clockwise direction. So we go from 1 to 2 this way, 2 to 3 that way. So this is going in an anti-clockwise direction. And so we know that anti-clockwise is S. It's not making a right-hand turn in the steering wheel. And so that is going to be the S compound. There we go. Okay, let's look at the next one. The next one, we've got a hydrogen at the back here. We've got a deuterium atom. So this is the first time we've looked at an isotope of one of the elements. So deuterium is just hydrogen with a neutron and a proton in the nucleus. So it has an atomic mass of 2. And then we have a carbon atom versus a fluorine. Now, I keep on telling you that it's the atomic number that is important for assigning priority, but the atomic number of hydrogen is the same as the atomic number for deuterium. So actually, in cases like this, it's actually the atomic mass. So the atomic mass of deuterium is 2, whereas the atomic mass of hydrogen is 1. And so hydrogen is the lowest priority and deuterium is the second lowest. So it's 4, 3, carbon next, and then highest priority is fluorine. So we get the lowest priority group at the back, and we're going in a direction from 1 to 2, which is clockwise. Clockwise equals R, so this compound is the R configuration. There we go. Now, just going through the next couple, we've got a hydrogen here. We've got carbon versus carbon, so we're going to have to do a search out along the chains there. If we keep on going out along the chain, we've got 2 hydrogens versus 2 hydrogens and a carbon as we go out along the chain. Then we've got, from that carbon, we've got a hydrogen and 2 carbons attached to it versus 2 hydrogens and 1 carbon. So if that's not clear, let's just expand that out a bit further. So this group here is a carbon with a hydrogen and a hydrogen attached, and then a carbon with a hydrogen. And here we've got these 2 methyl groups in brackets with a 2 next to it. That is 2 methyl groups like this. So as we go out along the chain, we're going to have this position here is the same as over here. So we're going to have this carbon then goes to this one, and that carbon here has a carbon, and a hydrogen attached to it. Okay, so if we look at the one below it here, we've got a carbon going to a hydrogen, we've got a carbon going to a hydrogen, and a carbon. So this was the point along the chain in which we're comparing to this one over here. And at that point, that carbon is attached to a carbon, a hydrogen, and a hydrogen. So this one here wins because we've got the first point of difference is this carbon here versus this hydrogen here. So this ends up being the higher priority substituent rather than this one. So 1, 2, 3, and 4. We've got the groups going in a anti-clockwise direction with the lowest group at the back, and so this is an S compound. There it is, S. And finally, we've got this situation over here. So let's look at this substituent here. We've got a carbon going to a nitrogen with dummy atoms, like this. Okay, let's compare that to this one over here. We've got a carbon going to an oxygen and a hydrogen, and then expanding out the double bond, we've got a phantom oxygen atom and a phantom carbon atom. And then if we look at the remaining one down here, we've got it going to a carbon, which goes to a hydrogen, and a carbon with those hydrogens attached. So in each case, we can just go along the chain until we find the first point of difference. Okay, so let's look at each of these. The first atom we get to in each of the circled substituents is a carbon atom, so go one further out along the chain. Here in green, we go one further out along the chain and we get to a nitrogen, and a nitrogen. All right. Here in blue, we go one further out along the chain and we go to an oxygen, and a hydrogen. And in red, we go one further out along the chain from here. We get to these two hydrogens, this carbon, so we get carbon, hydrogen, and a hydrogen. Okay, so looking at a periodic table, we know that oxygen is higher priority than nitrogen. And so that whole substituent in blue is going to be the highest priority substituent. And then comparing this group here to this group here, carbon is lower priority than nitrogen, and so this will be the next highest priority. So we're going to have priority order of 1 for this, 2 for that, and 3 for that group. We've got the lowest priority at the back, the hydrogen, so we're going in a clockwise direction, and so this must be the R configuration. And there we have it, R. Okay, so let's look at a few more examples. So here we've got absolute configuration of some molecules that have branching. So let's look at the first one. We've got hydrogen is going to be the lowest priority. The next one, the next lowest is going to be this one here. It's pretty easy to see that a methyl group, when we expand on that, we're going to get to only hydrogens. So that's going to be the next lowest. And then we've got a choice between the top and the bottom there. So let's look at the top group. We've got expanding out from this carbon, we've got a oxygen, a carbon, and a hydrogen. So that's carbon, oxygen, and hydrogen. I've just listed them in order of atomic number. And then if I do this one down here in green, we've got a hydrogen, an oxygen, and a carbon. So we've got oxygen, carbon, and hydrogen. So we go further out along the chain of highest priority. So we go from the oxygen across to a carbon atom. So this methoxy group here is an OCHHH. The thing that is directly attached to that oxygen is a carbon atom, and so therefore the only thing we list is a carbon atom there. Whereas on the green group, we're going out from the highest priority group to a hydrogen. So that hydrogen is versus a carbon, and so we know that this group will be the higher priority of those two. So this should be 1, this whole group here, and this group over here should be 2. And so we've got the lowest priority group at the back. We're going from 1 to 2 to 3 in an anti-clockwise direction. So anti-clockwise is S. So that should be the S isomer. Okay, so let's go to the next one here. We've got the lowest priority group is the hydrogen, 4. Next lowest is the methyl group, 3. And then we've got these, it's very similar to before, but we've got 2 carbons versus each other. Further out along the chain, we've got on this side, we go from carbon to a oxygen, a carbon, and a hydrogen. And then from the oxygen, we go to a carbon. Down the bottom here, we have a similar situation. We have a carbon going to an oxygen, a carbon, and a hydrogen. That oxygen goes to a carbon. So once again, we've got the same situation. And each one of those groups, in this case, goes to a hydrogen, a hydrogen, and a hydrogen. And in the green case, it goes to the same, a hydrogen, and a hydrogen. So we've run out of options along this highest priority route, so we're going to go to the next highest priority route. So let's have a look at this. Now we've got this carbon atom here goes to 3 hydrogens, hydrogen, hydrogen, and a hydrogen. If we look at the blue substituent, that carbon here goes to a carbon atom, this one here, and 2 hydrogens. Okay, so this is the higher priority group, higher than this one over here, and so therefore this blue group will be the higher priority than this green group. Okay, lowest priority group is at the back. We go from 1 to 2 in a clockwise direction to 3. So clockwise, that means this molecule must be the R configuration. Okay, and then we have it, R. All right, let's look at some multiple bonds. Here you can see that this molecule has the lowest priority group at the back. A methyl group is easy to pick out as being the next lowest priority. And then we've got a carbon that goes to a carbon, a hydrogen, and a hydrogen. Okay, so let's look up here. In blue, we've got a carbon atom that goes to a phantom carbon atom, another carbon, and a hydrogen. So here we've got the hydrogen, here we've got the carbon, and here we've got another carbon because of the fact that it's a double bond. Okay, so we've got the first point of difference here, so that gets the higher priority. So this is going to be 1, and the red group is going to be 2. We go from 1 to 2 to 3 in an anti-clockwise direction, so this must be the S compound. Okay, so let's look at the final example here. We've got a molecule with more than one multiple bond. So we're going to have to do some expansion using these phantom atoms. So the lowest priority group is easy to pick, it's the hydrogen, but the other 3 substituents, don't rush into this. You need to take your time and make sure that you've got this right. So we've got, we'll do this group here first. So we've got a carbon atom that expands into 2 phantom carbon atoms, and then the next one along the chain is a carbon. So let's have a look at that. That's going to be like this. Let's do this one in blue. So that group is going to expand from a carbon into a carbon atom that's bonded to, plus a phantom carbon atom from the double bond, plus a hydrogen. So it's expanding that out. And then let's do the last one in green. This one here is going to be a carbon that expands out into a carbon atom here twice. So this carbon, this group here is bonded to 2 methyl groups. So we're going to have a carbon, and then the hydrogen. So that's how that's going to expand. So we can immediately see that the highest priority group is going to be this one, because we have a carbon, versus a carbon, and a hydrogen, or a carbon, and a hydrogen. Okay, so now we need to pick apart the blue versus the green, because we've got the same there. So here in the blue, we've got a expansion from the top carbon here is this position over here. So it expands out into a phantom carbon atom from that double bond, plus a hydrogen, Whereas down the bottom here, our first one of these hydrogens expands out into a hydrogen, and a hydrogen. So here we've got a point of difference. We've got a hydrogen here that corresponds to a carbon here. So this is the higher priority group. And so this must be 2, and this one must be 3. So we've got from 1 around to 2 to 3 is going in anti-clockwise direction. So this must be the S compound. Okay, so hopefully that gives you a bit of guidance about how to assign the R or the S configuration to chiral molecules. So we can assign R or S to a chiral center based on following the Cahn-Ingold-Prelog rules. We spot the 4 different groups, we assign priority to each one, we put the lowest priority group at the back, and then we go in order of priority 1, 2 to 3. If it's clockwise, we're making a right-hand turn in the steering wheel, and therefore it's going to be the R configuration. If it's anti-clockwise, then it's S configuration. Okay, and don't forget to draw those phantom atoms when you've got multiple bonds. Okay, good luck with your R and your S, and thanks for watching.